How? Okay. Whoa. How, 1 2 1 2. um. How about now? Can anybody other than Jared hear me at this moment in time? Just out of curiosity. Oh, there we go. Okay. Okay. Awesome. Whoa. Might be a little loud. Okay. um. Okay. Right, well, so that explanation that I just dove into. Okay, awesome. Awesome, awesome. So, in recap of all the things I just said. So, I was here in my office. I apologize for the late start. I was here in my office working actually on exam 1. And I looked up at the clock and it was like right at 1, and of course, so I quickly fire up the stream, and the microphone drivers decided to fritz out on me, and so I had to restart the both computers and do all sorts of fun stuff. So I apologize for there might be a high pitched squeal in the background. We might just have to live with it today. Okay, but it's probably not you, Murat. Anyways, a couple things to say before we get started. Let's see, what was I gonna say? Oh, right. If any of you have sent me an email, I haven't had a chance to check them yet today, so you will be hearing back from me. Today, apologize for the wait, but I'm still sorting through. Well, I haven't started sorting through emails. There's a lot of spinning plates going on as I start this week. One thing, excuse me, that I did want to bring to everybody's attention is that we will be. There we go. Exam 1, which technically it's our second exam if you count the prereq exam, but exam 1 is dropping this Friday, so it is. We are on track to launch at 9:18. It opens at, not H, at 11:59 p.m. It's the open, and its close is a week from today, so 9/21 at 11:59. PM as well. I will have more information, especially on Wednesday. I'm currently in the process of writing it. I kind of have a rough outline, so I have an idea of how long it's going to be, and the content it's going to cover. So again, I'll have more information about this in the future, and by the future, in the next 48 hours, as well as like a detailed post of things to study. But there's a couple things that I wanted to touch on, and the first is that in this class, all exams are cumulative. All right, so all exams are cumulative. It'll cover everything that we've covered up to this point. Just because you were tested on something on the prereq exam, that material is totally fair game for this test. Specifically, it will cover. It will pull from some of the prereq exam material. Especially in the departments of sig figs, unit conversions, There may even density might even sneak its way onto this exam somehow. It'll cover everything we talked about in chapter 2 and chapter 3. All right, we should be finishing chapter 3, or at least getting close to it. The remaining things that we have to talk about in chapter 3, we've talked about empirical formula, but we are going to cover how to calculate a molecular formula from an empirical formula. And we're going to talk about balancing chemical equations. All right, so those two things are the last two things in chapter 3 that we have left to cover, and those things will be on the exam. So chapter 3 will be the cutoff. Chapter 4 will be exam 2 material. Jared, great question. The exam will be timed. I don't know how long it is yet because I don't know the total problem count. But there will be more logistical information coming out in the next few days. So keep your once I've finished it, I will write a Canvas announcement, kind of breaking down exactly how much points are associated with each subject, and let's see, the number of points in each subject. Yeah, how many problems, how much time you'll have to take it, all that good stuff. Yikes! Well, that was terrifying. All right. So let's, okay, that's unstable. Let's see if we can find a better, there we go. So we on, totally, and if anybody has more questions, totally hit me up in office hours tonight. I'll answer all of, all of the questions about the exams that you have. Let's save those for office hours, because we're a little bit late starting in today, and we've got some lecture stuff to cover. Though I will say, Becky, I'll answer your question. Why are we having tests over the weekend when it would normally be in person? Well, Bailey, this class that you're in is listed as asynchronous. That means that there is no, even though there's a scheduled class time, you're never required to be present at any given time. And so because attendance isn't required, logging in at a specific time isn't required, the way exams are administered is there will be a window in which they're open, and you can take that time at your convenience anytime in that window. And if you look at the syllabus, all of the exams open on a Friday and close on a Monday. So every single test you take in this class will be over a weekend. All right, let's go ahead and, so we were last in lecture on Wednesday, and we were calculating empirical formula, and we had, in an example, we had calculated the empirical formula for a compound that contained both silver and oxygen, and we had found that the empirical formula was Ag2O, that this was the empirical formula. All right, now these problems, these empirical formula problems, will often be presented in two steps. The first step will be use the information like we were given to calculate an empirical formula, right? We were given the mass of silver, mass of oxygen, and that is a typical part one of these problems. In part two of this style of problem, you will be asked to calculate, well, actually here, hang on. in part 2 of these types of problems, first you'll be given the molecular weight, all right, what the molecular mass of the compound is, and you'll be asked to find the molecular formula. All right. So you'll be given the molecular weight and you'll be asked to find the molecular formula. Now, to find the molecular formula, hang on, I need to pull up my so to find the molecular formula, here you need two things. You can find the molecular formula if you first know the empirical formula, and second, you know the molecular weight. Oops. All right, and here's how you use those two pieces of information to find the molecular formula. Remember, the difference between a molecular formula and an empirical formula is this. For an empirical formula, it's the simplest whole number ratio, right? So an empirical formula, for example, could be CH, right? One of each. There's a 1-to-1 ratio of carbon to hydrogen in CH. A molecular formula is not the simplest whole number ratio, it's the actual atom count. So in the molecular formula, for example, the molecular formula for this empirical formula could be C6H6. All right? And how you go from the empirical formula, the only difference between the empirical formula and the molecular formula is an integer factor, right? You take the empirical formula and in this case multiply the atom count of the empirical formula by 6, right? By a number, in this case it's 6, to get the molecular formula, right? You need to multiply it by the number 6, and that's how you go from the empirical formula to the molecular formula, all right? So all it boils down to, once you know the empirical formula, you just need to find that integer factor, and once you have it, you can calculate the molecular formula. The way you find that integer n, is equal to the molecular weight divided by the empirical weight. Now, we've talked about molecular weight already in this class. We haven't really talked about empirical weight at all, right? And for this problem, the molecular weight would be 6 times the atomic mass of carbon plus 6 times the atomic mass of hydrogen, right? Whereas the empirical weight is the same thing, but instead of using the molecular formula, you're using the empirical formula. So it'd be 1 times the atomic mass of carbon plus 1 times the atomic mass of hydrogen, and that is how you calculate that scalar factor. All right? Now, for the previous example, the example that we left off on, we have an empirical formula of Ag2O, right? And step 2 of that problem, once we have the empirical formula, would go like this. The molecular weight of this compound is 231.375 AMU. What is the molecular formula? Let's see. All right, what is the molecular formula? Here, hang on one second. My fan's being a little loud in the next room. Hey, babe. All right. There we go. Okay. So, what is the molecular formula? So, as we know, we need to find the scalar factor. We know that the molecular formula is going to be Ag2 times whatever that scalar factor is, and then O1 times whatever that scalar factor is. And we also know that that value for N is going to equal the empirical weight, the molecular weight, which we've been given, 231.375 over the empirical weight. All right? Molecular weight over empirical weight. So to find what this value for N is, we need to calculate the empirical weight. That is what we're going to do next. Now, flipping over the closest periodic table that I have available to me, silver. Let's open a new layer. There we go. Silver has a atomic mass of 107.87. Oxygen has an atomic mass of 16.00. And we have 2 silver atoms in our empirical formula. So we go 107.87 times 2 plus 16.00. All right, so that gives us not a molecular weight, an empirical weight of 231.74 AMU. And now we can calculate the scalar factor we need to multiply our empirical weight by. All right, so we have our molecular weight 231.375 divided by 231.74. Our units cancel out because this is just going to be a number. 375 divided by 231.74. So the value that my calculator is giving me is 0.99842 all right? And you should never expect these numbers to come out like completely clean, because we're dealing with raw data, right? We're dealing with information that is measured, and so the numbers will never come out to be perfect integers. However, when you look at this number, what integer is it close to? This is approximately 1, all right? That is what that integer is. And so, to take our empirical formula to our molecular formula, we need to multiply every atom in our empirical formula by 1. So our molecular formula is Ag2O1. All right, for this problem, the empirical formula is the same as the molecular formula. And that will always be the case when your multiplication factor, that integer that you solve for, is 1. The empirical formula and the molecular formula will be the same. All right? It was in this case, and I wanted to do an example so you could see that that was indeed a possibility. But it will not always be the case, as we'll see in our next example. All right, so let's do another one of these. All right, so another thing that will be different in our first empirical formula example, we saw that that we were given information about the elemental analysis in terms of mass. We were told that we had 1.651 grams of silver and 0.1224 grams of oxygen. That's one way elemental analysis is reported, but it's not always the case. Sometimes you won't be given masses, you'll be given percent mass. So, so in this example, a molecule of caffeine is composed of 49.48% carbon, 5.19% hydrogen, 28.85% nitrogen, and 16.48% oxygen by mass. This problem has two parts. Part 1 is determine the empirical formula for caffeine. And then part 2, determine the molecular formula if the molecular weight of caffeine is 194.19 AMU. All right, so we have a two-part problem. But first, the information, the data that we're given in this problem is different than the one that we were given in the last problem. The last problem we were given actual masses, but here you can see we're actually given mass percents, right? We're given the percentage of each element and we're told it's percent by mass. All right, now when you're given percent by mass, to solve this problem, we need to assume, you can assume any mass of your sample, but it's easiest if you assume, if you assume 100 grams, and here's why. If you have 100 grams of a sample, a 100 gram sample, then if carbon is 49.48%, then you'll have 49.48 grams of carbon. So assuming 100 grams means that you can treat each percentage as just a mass in grams. It makes the calculation easier. So we can literally take each percentage and write them out as the actual amount in grams. And so that's just a simpler way. Again, you could assume 13 grams if you wanted to, but it's, and you'd still get the right answer actually if you did that, but it's easiest to just assume 100. All right, now, as we know, to calculate the empirical formula, in the empirical formula, the ratio between each atom present is a molar ratio. So for each of these mass quantities, we need to convert our grams to moles. So we use the atomic mass of each element to convert from grams to moles. All right, and again, you can find all of these on your friendly neighborhood periodic table. I'm using the one that is closest in proximity to me at the moment. All right, so let's see, let's crunch some numbers. 49.48 divided by 12.01 comes out to be 4.1199 moles of carbon. 5.19 divided by 1.008 comes out to be 5.41488 moles of hydrogen. Again, with this type of problem, you don't have to really worry about sig figs because we're all going to round to an integer at the end. The one thing that can mess you up, though, however, is rounding too much too fast. So I just like to write them with 4 decimal places, and usually it works out all right. 0.02592 moles of nitrogen, and then we have, let's see, 16.48 divided by 16 comes out to be 1.030 moles of oxygen. All right, and again, remember, we're trying to find the empirical formula here. We're trying to find C. We've got a certain amount of carbon, hydrogen, nitrogen, and oxygen. Let's see. So we've got variables under all of these elements, and the value for those variables come from our molar quantities here. All right, so moving on to work our empirical formula, we're going to have C 4.1199, H 5.1488, N 2.0592, and O 1.030. All right, so this is the correct ratio for our empirical formula, but as we know, we need to get integers in here, right? We can't have any decimals, and the first step we take is we divide all of these by our smallest number. That'll turn our smallest number subscript into a 1. So oxygen, that'll just be one of them, and then it'll change everything else. So let's crunch these numbers. So for carbon, 4.1199 divided by 1.03 gives us, I'm getting 3.9999. All right, that is just a 4. Hydrogen, 5.1488. Or here. You know what? I was going to skip this step, but I'm going to write it out so you can see it. So this is, this is 3.9999. H, if we take 5.1488 divided by 1.03, this would be 4.9988. H, N, 2.0592. This would be 1.9992. And oxygen is going to be simply a 1. All right? So here, again, you're not going to get clean integer values except for that first one. So you have to look at them and go, okay, what integers are these, or what fractions are we dealing with? And here, we're dealing with C4, H5, N2O. All right, this is the empirical formula. For the thing that we put in our juice every morning. This is the empirical formula for caffeine. All right, and that is part A of this problem. All right, or part 1. Part 2 is we're asked to find the molecular formula. All right, in order to do that, we need to calculate our empirical mass. All right, then we can divide the given molecular mass by the empirical mass. So our empirical mass will go like this. Carbon has an atomic mass of 12.01, hydrogen 1.008, nitrogen 14.01, and oxygen comes in at a cool 16. Now in our empirical formula, we have 4 carbons, 5 hydrogens, 2 nitrogens, and 1 oxygen. So 1.008 times 5 is 5.040. 14.01 times 2 is 28.02. Oxygen is still just 16. And carbon is 48.04. All right, so adding these all together. Wait, hang on. 48.04 plus 5.04 plus 28.02 plus 16 comes out to be 97.10 AMU. All right, that's our empirical mass. And we can find our integer value that we need to multiply our empirical formula by taking the ratio between the molecular mass and the empirical mass. All right, so 194.19 divided by 97.1 comes out to be 1.999,89701. All right, and so this integer is actually just 2. So now we can take our empirical formula, which was C4H5N2O1, and we can get our molecular mass. Sorry, not our molecular mass, our molecular formula, by multiplying everything by 2. So C8H10N4O2, this right here is the molecular weight. Not the molecular weight, excuse me. The molecular formula for caffeine. All right, so that is the business. All right, that is the molecular formula of caffeine. Now you've seen examples of both starting with a mass, right? Here's a mass of silver, mass of oxygen, or starting from percent mass and how to get there in either instance. Okay, Angelina, let me see. Is there a certain value, like within 0.001, where we can just round? So now I have to do a fraction thing. Angelina, great question. There is no like numerical value. Like if it's within, there's no parameters. You just kind of have to eyeball it, which I know is always an uncomfortable answer to receive as a student. But if it's close to an integer, like if it's in the 0.9s or the 0.0, like zeros, then you're going to round to the whole integer. If it's close to 0.7, all the fractions we talked about, 0.75, 0.67, 0.5, 0.33, or 0.25, those are the ones where you're going to have to use the fraction situation. But as it was here, a 1.9, that's just going to be 2. But that is a great question. Okay. So that is, let's see. Will. Okay, Will. That is an excellent question. That is an excellent question. If I ask you to determine the molecular formula, then yes, I have to give you the molecular weight. There's no way for me to expect that of you. There's no way you can know it. That being said, I could give you information to calculate an empirical formula, give you the molecular formula, and then ask you to... Oh, wait, no, that would be dumb. I had thought of an example where I wouldn't have to, but I'd ask something different. But yeah. Yes, the answer is yes. There's no way you would have to come up with the molecular formula on your own, based on the empirical formula, because it's impossible to know that. So do not fear. Okay. Let's move on. The last thing in chapter 3 that we have to cover is we need to talk about balancing chemical equations. All right, balancing chemical equations. Totally. Okay, let's take a look here. So, a little bit of, just to make sure we're all on the same page, when you have a chemical reaction, there's a couple things involved with a chemical reaction. So, for example, you could have a reaction for the combustion of hydrogen, right? Where you have hydrogen gas plus oxygen gas produces water vapor. All right, now this is a chemical equation, a chemical reaction, and there's a couple things I want to point out. On the left side of the arrow, these are our reactants. And on the right side of the arrow, these are our products. All right? One goes into another, and then here, these little parentheses and subscripted dudes, these are called phase symbols. And they tell you what phase of matter each product or reactant is in. G is for gas, S is for solid, L is for liquid, and AQ is for aqueous. Which aqueous simply means that whatever it is dissolved in water. So when you have something in the aqueous phase, it's just been dissolved in water. All right, that's the basic breakdown, which we've all seen this in our prereq courses, but I just wanted to touch on it to make sure that we are all on the same page. Now, the chemical equation that I have written, there's something fundamentally wrong with it. All right. In a chemical reaction, matter is neither created or destroyed. All right. You can't make matter. You can't destroy matter. It can only change form. But one thing you'll notice is there is more mass on the reactant side as written than there is on the product side. And you may be going, what do you mean? Well, take a look at your atom count. On the reactant side, there are 2 hydrogen atoms and 2 oxygen atoms. On the product side, there is also 2 hydrogen atoms. There are 2 hydrogen atoms, but there's only 1 oxygen atom. As of right now, as written, this reaction is violating the law of mass conservation, right? Which says that matter is neither created or destroyed in chemical reactions. This reaction as written has a name. This is called an unbalanced chemical equation. All right, this is an unbalanced chemical equation, and it is never okay to leave a chemical equation unbalanced. So when you encounter one, it's up to you to balance them. All right, you need to balance your chemical equations before we can use them in any sort of calculation. And so we need to go over how to balance them. Now, there are two types of numbers that you run across, all right, in chemical equations. These little guys, the subscripts, right here, you can never change. All right? Never change these dudes. Because if you do, you're actually fundamentally changing the chemical reaction that you're talking about. The reaction between hydrogen and oxygen to produce water is different than, for example, the reaction of hydrogen. Oops. It's different than if, say, you were to write H2O2. This is a compound called hydrogen peroxide. All right? And if you altered the subscript on water to make it a 2, then it's a different chemical equation, all right? So you're never allowed to change your subscripts in a chemical equation. You are, however, allowed to change the numbers that each compound are multiplied by, because that doesn't change the reaction. If you change, right now we have one hydrogen molecule, one oxygen molecule, producing one water molecule. Changing that doesn't change the reaction that's going on, it just changes the quantity of reactant or product. So these numbers right here have a name, and that name is, these are called stoichiometric coefficients. And you are allowed to change these, all right? So you can't change the subscripts of any reactant or product, but you can change the stoichiometric coefficient, because that just says there's more than one of each present, all right? So let's use that information to now balance this chemical equation. So again, I'm just going to take an inventory. On the reactant side, there's 2 hydrogens, 2 oxygens. On the product side, there's 2 hydrogens and 1 oxygen. Well, what's unbalanced right now is my oxygen count. I have 2 oxygens on the reactant side, only 1 oxygen on the product. I need 2 though, right? The only way to get 2 is if I produce 2 water molecules. Now this changes my oxygen count, but you'll notice it also changes my hydrogen count. Now I have 2 oxygens on my product side, but I also have 4 hydrogens. So we just fixed a problem by creating another problem, right? Now my hydrogen count is imbalanced. But oxygen's good, so now I have to fix the hydrogen problem. Well, right now I have 4 hydrogen on my product side, but only 2 on my reactant side. It looks like I need to multiply hydrogen, H2, by 2, and now that these are the same on both sides of the reaction, we say that this chemical equation is balanced. All right? This is a gigantic part of pretty much everything that we're going to do this semester. All right? Balancing chemical equations, once introduced, never goes away. And this is something you need to get proficient at. I'm going to work several more example problems. But if you're rusty, and you'll remember doing this from your prerequisite class, but if you're rusty or if you're uncomfortable, you really want to get this in. You want to soak this in because, as I said before, we are going to be doing this for the rest of the semester. And if you can't, this is the first step of every multi-step problem I'll ever test you on. And if you can't get this right, it will mess up your subsequent answers. So I'm not exaggerating when I say that everything hinges on this. All right, let's do another example. Let's balance each of the following chemical equations. So here's sodium. Here's a reaction where sodium reacts with HCl to produce hydrogen gas and aqueous sodium chloride. All right. The first step to doing any of these is take an atomic inventory of both the reactant side and the product side. We've got sodium, hydrogen, and chlorine on both sides of this chemical equation. And we have on the reactant side one of each. And on the product side, we have one sodium, two hydrogen, one chlorine. All right. So hydrogen is initially the problem, right? We've got two on our product side, but only one on our reactant side. The only way to fix this is to multiply HCl by 2. This will balance our hydrogen, but you'll notice it'll mess up our chlorine. Now we have 2 chlorine on the reactant side, but only 1 on the product side. So we have to bounce over to the products and fix it. The only way to fix it is to multiply sodium chloride by 2. This balances chlorine, but throws sodium out of balance. All right? So again, now we bounce back over to the reactant side and we go, okay, we've got 2 sodium on the products. We need 2 on the reactants. We need to multiply sodium metal by 2. And this balances the chemical equation. All right? Okay. Let's do another example. Let's balance the following chemical equation where nitrogen gas reacts with hydrogen gas to produce ammonia vapor or nitrogen trihydride. All right, now here, again, we start by taking our chemical inventory. You have nitrogen and hydrogen on both sides of this chemical reaction. On the reactant side, we have 2 of each. On the product side, we have 1 nitrogen and 3 hydrogen. Now, you'll notice both things are out of whack in this chemical equation. And you'll also notice that with nitrogen, 1 evenly goes into 2, so that's nice. But 3 does not, and 2 don't go into each other evenly. Now you may be wondering, where do I start? What do I start with? And technically it doesn't matter, but here's the beautiful thing about balancing chemical equations. It is the rare opportunity where life actually rewards you for taking the path of least resistance. So my advice to you is pick whichever one is easy, whichever one evenly goes into the other, and ignore the thing that's hard. Just move forward believing that it'll work out in the long run. Let me show you what I mean. I'm going to ignore the hydrogen situation here and just go for nitrogen. 1 goes into 2 twice, right? So to get 2 nitrogen on the product side, I need to multiply NH3 by 2. All right? This balances nitrogen, changes my hydrogen count from 3 to 6. Now check out the hydrogen situation. 2 does go into 6 evenly. So to balance hydrogen, I just need to come back and multiply H2 by 3. All right? And this is my balanced chemical equation. All right. Let's do another example. Let's go ahead and do N2H4, aqueous N2H4 plus O2 reacting to produce water vapor and nitrogen gas. All right, here we've got 3 players. So again, we're going to take our atomic inventory on both the reactants and the product side of this equation. We've got 2, 4, and 2 on the reactant side. On the product side, we have 1, 2, and 1. All right. Nitrogen seems pretty straightforward, right? We've got 2 on the reactant side, 1 on the product side. Whoa, excuse me. No, we don't. Sorry, the product isn't nitrogen, it's nitrogen gas. So there's 2 of them. So actually, nitrogen's totally balanced. Let's look at oxygen. We have 1 on the reactant side, 1 on the product side, 2 on the reactant side. So we need to multiply H2O by 2 to get balanced here. And that balances the whole chemical equation. Now, normally, when I see something like this, where it's like, oh, just multiply one thing by 2 and that solves the whole problem. As a student, I would always kind of like give my professor the side eye, because I'd be going, okay, it looks like you're doing that thing where you're just picking the easiest possible example, but the one on the exam is going to be insane. And I want to let you know that actually this is typical. You will see problems like this, chemical equations like this, that you will be asked to balance that'll be this easy. I have even on the exam put equations, also balance this chemical equation, and it's already balanced. All right. So I've even done easier. I've put easier on tests, and I will do that caliber of thing for you. The point is, the reason why I'm bringing this up is, 1, this is accurate to what you'll be tested on. There will be harder ones, but there will be soft ones as well. And when you get a soft one, it's me giving a gift to you. So don't overthink it. Don't second guess yourself. Don't think, whoa, this is too easy. It's got to be harder than that. If it makes sense, just roll with it. All right? Don't change your answer. Okay. Let's see. We have a couple more examples, and then we will be done with chapter 3. First, with this equation, with this next example, I'm going to show you a method that might seem overly complicated for the problem. All right? You might see this and go, I don't need to know this. I could solve this problem another way. And I don't doubt that you could. All right? The method that I'm going to show you for solving this reaction will seem overly complicated. But the reason why I'm teaching you this method is because there will be examples in the future that'll be much harder to balance unless you know this method. So we're going to do this here. And if it seems overly simple, just roll with me, because you're going to need this method for the next example. All right? Let's take our atomic inventory. On the reactant side, we have 2 of each, 2 hydrogen, 2 oxygen. On the product side, we have 2 hydrogen, but our oxygen count, we have 1 oxygen coming from water and 2 coming from oxygen. 1 plus 2, you may be going as 3. But trust me, you want to keep these separated here. All right, and here's why. Here's the problem. It's impossible. Well, let me rephrase that. here's the thing. Hydrogen is perfectly balanced, right? We only have one element up in here that isn't balanced. And you'll notice that we have elemental oxygen, O2. So all we need to do is multiply O2 by some number, all right? Some number, so that when we multiply O2 by this number, it'll make our oxygen count on either side of this equation even. What is this number, you may ask? Well, let's do a little algebra. First, we got to subtract 1 from both sides of this equation. We get 1 is equal to 2 times said number. Now let's find this number. Divide both sides by 2. And we get that this enigmatic number is 1/2. Watch what happens when we plug it in to our balanced chemical equation. If you multiply 2 by 1/2, then you get 1 plus 1, and now our oxygen count is balanced. It's awesome. The problem here is this. You never, or no, I should say, all stoichiometric coefficients, remember that is, those are the numbers out in front of every species in your reaction. All stoichiometric coefficients must be integers. All right, all stoichiometric coefficients must be integers, and we have one that's not. We have that 1/2 there. So you can use a fraction to balance your chemical equation, but you can't leave it there. Once you do use a fraction for balancing, you need to multiply the entire reaction by the denominator of the fraction you used. And once you do, then you'll get your balanced chemical equation. So you have 2. Once we multiply this through, the balanced chemical equation will be 2 molecules of hydrogen peroxide decompose into 2 molecules of liquid water plus 1/2 times 2 is just 1 molecule of oxygen. All right, so you're allowed to use fractions to balance your chemical equation, but after it's balanced, you've got to get rid of those fractions by multiplying everything in your equation by the denominator, whatever that may be. Now, we don't have time to do this last example, so we are going to open up lecture on Wednesday. We're going to open up lecture on Wednesday with the following chemical equation. Give this a crack. Try this in between now and lecture, and see if you can make it work. And the hint is you'll need to use that fraction method that I just showed you with the previous example. See if you can balance the combustion of benzene, so the reaction of C6H6, which is a liquid with O2 gas, to produce gaseous carbon dioxide and water vapor. All right, so see if you can balance this chemical equation. And we'll give this a try all together on Wednesday in lecture, or if you try it and you want to know sooner, drop by in office hours and we can also do it then. All right, again, I apologize for the technical difficulties. Thank you all for being gracious. I'll see some of you, anyone who wants to hang out tonight in office hours, and the rest of you I will see not tomorrow, because tomorrow's Tuesday. I'll see you in lecture on Wednesday. Have a good 48 hours, dudes. Later.